So section 4.4, we're looking at radical functions. I think we're just going to spend pretty much one day on those. Next section we do is 5.1, and we're going to look at exponentials. And 5.4 is on logarithms. So we're really finishing up the last three types of functions for the algebra part of the class. Okay, some things we'll do with them, we'll graph them. And then we'll also have basic equations to solve. All right. So let's take a look at radical functions. So those are all examples of radical functions. Y equals square root x minus 2. That's kind of a simpler one. Y equals the cube root of x squared minus 1 plus x. Much more complicated one. Basically, any expression that has a root in it is called a radical, or is called a radical expression. Now, the most common root we see a lot is a square root, but you can have square roots, you can have cube roots, you can have all kinds of roots. And so anything that has this that I'm highlighting makes it a radical expression. Now the key is that that little number that you put right here where n is, like in the problem up above, it's a 3. That number has to be a positive integer greater than 1. Okay. So the smallest kind of root that you can take is a square root. There's no such thing as a first root. Never heard of that. Maybe a first root would just be the number itself. Okay. That doesn't really make sense. But square roots, cube roots, I'll show you how to type them in on the calculator and how to graph them. So this thing that I just circled is called a radical. The number that you put on the outside of the radical, kind of as a small number in that little space right there, that is called the index of your radical. Now, in a problem like the one I just circled, there is no index written there. Does anybody know what we assume the index is if it's not written? Yeah. It's a 2, right? It's a 2. If you don't put an index, we assume it's a square root. The thing that you put under the root, okay, basically, what are you taking the root of? So like if I did this, 6 is called the radicand. It's basically the thing that you're taking the root of. And then the actual symbol itself, like the part that has like the check mark and the horizontal line on top, that is called the radical sign. Okay, so any questions on the terms radical expression, index, radicand, or radical sign? Just a few terms that we might throw around a little bit as we go through it. Okay, so as I said, two big things we're going to do today. We're going to graph roots. There's a pattern. Whether you graph an even root or an odd root, even roots kind of all look the same. Odd roots kind of all have the same look. And you can stretch them and compress them a little bit, but we're going to kind of learn the basic patterns, and we'll do a little bit of equation solving. Okay, a little bit. Okay, we already said that. If you have no index written, always assume it is a 2. Now, radical expressions can also be written with fractional exponents. We don't really get into the proof why, but another way to take a square root is to raise something to the 1/2 power. Okay, so here's an example. Let's take the square root of 12. Get 3.46. Let's take 12 and raise it to the 1/2 power. Or 0.5, same thing. 3.46. Okay, so what I'm just trying to show you is that taking a square root or raising something to the 1/2 power is exactly the same thing. Same thing. Now, to do a cube root, you wouldn't raise something to the 1/2 power. Anybody know what you would do to do a cube root as an exponent? Yep.
1/3.
It would be the 1/3 power. Yep. Now you can't really make a lot of sense of that easily because, like, if you had 8 to the 3rd power, I mean, using the definition, it means to multiply 8 times itself this many times. Well, how would you multiply something by itself 1/3 of the time? It doesn't really make a lot of logical sense. You can either do something like do it twice or do it 3 times. How could you do something like in the middle, like 2 1/3 times or 1/3 of the time? So it's a little weird to have fractional exponents, but it works out. How about a 5th root? What fraction, bless you? What fraction do you think would be a 5th root? Yeah? 1/5. And watch what happens here. You still have the radicand, right? That never changed in any of them. But now you have the radicand, which is x to the 4th to the 1/5. Does anyone remember the rule when you have a power to a power? What you do with those two numbers?
Yeah. Multiply.
You multiply them. So by changing the 5th root to a 1/5 exponent, you actually can use a rule from Algebra 1 and write this expression a little bit more simply. It's a lot easier, I think, to plug in x to the 4/5 on the calculator than the 5th root of x to the 4th. But by the end of today, you should know how to type both of them in, so you could pick either one. This idea of having exponents instead of a root symbol, that's going to come up again when we do logarithms. Okay? So the most important one to remember is that square roots are to the 1/2 power. Okay, next thing. When we are solving equations, if they say solve for the principal root, it means they want one answer. Now, we should know that when we take a square root, how many answers are there normally? So let's do an example. What's the square root of 25? What times what is 25? And they got to be the same. Yep.
5 and -5.
5 times 5 is 25. -5 times -5 is also 25. Well, that's two different answers. Okay. When I ask you for the principal root, I want one answer. So we're going to break this up into two different cases. Whether or not you have an odd or an even number. So, if you are doing an odd root, you're basically trying to solve this equation. This is how I would explain it to someone in Algebra 1, except I'd put numbers in here. Okay? And I'll show you an example with numbers. Let's say that I wanted you to find the cube root of 64. I want you to find the cube root of 64. Look at that, and look at that. Just match up which letter is which. What's M in what I circled? Yep. 3. What's A? 64. So let's rewrite it like this. Let's rewrite it like that and watch what happens. X to the, you guys told me N was 3, and you told me A was 64. That's how I would explain to someone in Algebra 1 what a cube root means. I would say you are looking for a number that you can raise to the 3rd power and get 64 as the answer. So, anybody tell me what that would be? What times what times what? All the same. Gives me 64. Emily? 4. Yes, 4. 4 to the 3rd power gives you 64. So in other words, 4 is the cube root of 64. All right, so that's basically what you're trying to figure out. And if it's a fifth root or sixth root or whatever root it is, right? But that's how you can think about it if you don't know what a root means. Now, if n is even, there's another restriction on the radicand. It has to be greater than or equal to 0. Why? Think about a square root. What would happen if I try to take the square root of -5? Yeah.
It's imaginary.
It's imaginary, okay? We're not dealing with imaginaries. So anytime you're dealing with an even root, the radicand has to be positive. That is not true for an odd root. Like if I said, what's the cube root of -8? That's no problem, -2. -2 times -2 times -2. Cube roots can be positive or negative. Even roots have to be positive. So if you're dealing with an even root and the radicand is positive, I want you to give me the answer that is non-negative. Okay? So that's like a couple minutes ago I said, what's the square root of 25? Jared said 5 and -5. Well, if I ask you for the principal root, I want one answer, and I would want the answer that's non-negative. Right? So if I were to write this out, kind of the question I had asked earlier, it was x equals the square root of 25. Now it's invisible, but what's the index right there? What is it? 2. It's 2. Right? So you're basically trying to solve this equation. X to the index equals the radicand. And I know that there's two numbers at work. I want the one that's non-negative. 5. 5 to the second power gives you 25, which means 5 is the square root of 25. Okay. Any questions on that? So cube root, fifth root, seventh root, any odd root. Positive or negative answer, fine. Even root, I only want the positive answer. And if you follow those rules, no matter which case you have, we will all only get one answer for each problem. Okay? Even if there is another answer, we'll only get one. All right, so now I want to look at a table of square roots, and I want you to tell me whether it gets smaller or larger. What's your first thought? If you take the square root of a number, what happens to it?
Smaller.
Most people say right away, it'll get smaller. Let's try an example. Brandon, what's the square root of 4?
2.
2. Did it get smaller?
Yeah.
Sure. Right. So we got 2. Square root of 18. Let's look at that one. 18. Take the square root. 4.24. Eric, did that one get smaller or larger?
Smaller.
Yeah, it got smaller. Right. Let's look at this one. 1. Jacob, what's the square root of 1?
1.
Smaller or larger?
Be the same.
Stay the same. Didn't get smaller. So there's an example where you take a square root and it doesn't get smaller. Right? Let's keep going. Let's take the square root of 0.5. Now, think about this for a second. I want to multiply two numbers together, and I want it to equal 0.5. Let's say that you thought it had to stay the same. Right? Let's say, oh, well, if it's a decimal, maybe it just stays the same, 0.5. If you tried 0.5 times 0.5, what's 0.5 times 0.5? Or what's 1/2 times 1/2?
Like
Yeah.
2, 1/4.
It's 1/4. That's not 0.5. It's too small. So what does that mean about this number compared to the real square root of 0.5? Is that number too small or is that number too big? Yes. The real answer is what? The real answer is larger. 0.5 isn't big enough. In fact, when you take the square root of 0.5, look what happens. 0.71. you get a bigger number. If you take the square root of 0.2, 0.45, I'm just rounding it. But my point is, on these two, it actually got bigger. What do you think controls whether or not when you take a square root, it's going to get smaller or larger? Because sometimes it got smaller, sometimes it got larger, sometimes it stayed the same. What's going to control that?
I think if you're greater than 1, it'll get smaller. If you're less than 1 but greater than 0, it'll get bigger.
Yes. So decimals between 0 and 1, when you take the square root, they get bigger. Numbers bigger than 1, when you take the square root, they get smaller. Okay? So, let's take a look. In this part, you can type it in if you want to practice, or you can just watch me. I'm going to graph the square root of x, and I'm going to graph the fourth root of x. This is how you type in a fourth root. Type your index, press math, option 5. That's how you do a fourth root. Index, math, option 5. So, I'm graphing square root and fourth root, 2 even roots. Now, they're just in quadrant 1. So let's focus on that. So let's set that at 0. Let's set our y min at 0. And let's set our y max at 4. I think if I do that, you're going to notice something. That's the square root. That's the fourth root. Does anybody notice anything about those two? Any patterns at all? Yeah?
Both going to the right and kind of like leveling off.
Okay, they both only go to the right. Okay, if you notice when I was zoomed out, there was nothing in quadrants 2, 3, or 4. These are all in quadrant 1. Okay? So the domain on these is from 0 to infinity. Okay, right? Square roots, fourth roots, can't take the square root of a negative number. So it has to go to the right. All right, anybody notice anything else about the red and the blue graph? Yeah?
The red line starts off higher.
Yeah, when you compare square roots to fourth roots, or fourth roots to sixth roots, or however you want to compare it, which one is on top of the other depends. Are you before 1 or are you after 1? If you're after 1, the square root is bigger than the fourth root. When you're before 1, it switches. Okay? The fourth root is bigger than the square root. Okay? Now, if I put a sixth root in there, it would look something like this. It would be on top of everything in the section before 1, and then it would cross at 1, kind of like that. And it still goes up a little bit. It never really levels off. But that's what a sixth root would look like. Above everything before 1, below everything after 1. So maybe you've kind of noticed they all start at the origin and they all go through the point 1, 1. Okay. So let's write some of these things down. So 0, 0 and 1, 1 are common points to all even roots, unless you shift it. Of course, I could take a square root and shift it up, and then it wouldn't go through 0, 0. Okay. We will talk about shifting it later. Okay. Domain and range are both 0 to infinity. Starts at 0 and it includes it, and like Jared said, they head to the right forever. So those are some things you just want to notice with even roots. Next, we're going to take a look at odd roots. Okay, so I'm going to graph an odd root, and I just want you to tell me something that's very different. Doesn't matter what kind of odd root. Let's do a cube root. Okay, so to do a cube root, index, math, 5. That's how you do cube root. If you have an older calculator, it may not change the 3 to be a superscript like that. It might just leave it as a 3 in front. That's okay. Like it's going to on that one. But it still means the same thing, and you type it in exactly the way I just said. Okay, so cube root of x. Can somebody tell me something that's very different about that graph compared to types of graphs we just looked at? Yeah, okay.
It starts on the negative side.
Yeah, it starts on the negative side. This goes in both directions forever. The reason for that is because you can do cube roots of any number you want. You can go negative numbers or positive numbers. If I graph one other cube root or one other odd root, you might notice something else too. So let me do a cube root and a fifth root. There's your fifth root. What I'm going to do is I'm going to zoom in between -3 and 3, and then I think you'll see it a little better. So let's go -3 to 3. It's going to look a little distorted because I zoomed in. It also looks like it kind of breaks apart. It doesn't. It is connected. It's because the calculator can't draw things that are steep. All right, and I don't know if that's enough you can really tell. Let's go -3 to 3 on the x's. I think that might even be better because I'm trying to show you something. All right, so there's your cube root, and here's your fifth root. I don't really care about which one is on top of the other because they kind of switch places a couple times if you look closely. But does anybody notice something about like the intersections? Yeah.
They intersect at the -1, 1, 0, 0, 1, 1.
Yep, they intersect at -1, -1, 0, 0,
Yeah.
and 1, 1. So these cross 3 times. What's the domain here? Left and right, how far does it go? Oh, Chris?
Is there -50, 0?
Not quite. -infinity to 0 would mean it stops at the y-axis. Anyone help Chris out with that? What's the domain here? Like think about if you drew a vertical line and you drag it left and right. Ask yourself if it would miss the graph somewhere. If it would, then the domain is missing something. But look carefully at that one. What do you think? It is. This graph goes left and right forever. No matter where I put a vertical line, it's always going to hit it. Okay. So domain is -infinity to infinity, and so is the range. This graph goes up and down forever. You might say, well, doesn't it look like it's leveling off? Maybe we have a horizontal asymptote. You don't. Square root functions never have horizontal asymptotes. In fact, root functions don't have any asymptotes at all. None. Right. So like, if you did the square root of 20, you get what is that, cube root? I'm sorry, cube root. If you did the cube root of 20, you get 2.71. If you do the cube root of 50, 3.6. Cube root of 500, 7.9. It's just going up. It's not leveling off at anything. Cube root of 9,999 is 21.5. So it's going up to infinity on the y's. Okay, so when we sketch roots, we're really looking for 2 things. If it's an even root, you're looking for the start point and which way it goes. If it's an odd root, you're looking for the center point. And then it kind of does something like that. In general. Okay, so even roots have a start point. They go in one direction. Odd roots have a center point. and go both ways. So keep that in mind. All right, so we're going to look at transformations with all three types of functions we studied this week. Roots, exponentials, and logs. So let's label what the A, the B, and the C, and the D do. Can someone remind me what it does if you add or subtract inside your function? What kind of transformation? And your choices are, you got the vertical, shift and stretch, horizontal, shift and stretch. A, B, C, and D are each one of those. Yep.
The shift, that shifts it left and right.
So this is a horizontal shift. How about B? B is when you are multiplying inside the function. Yeah?
Vertical stretch.
Vertical is always stuff that's outside the function. So inside in this case means under the root. So vertical is going to be when we get to C and D. But what about B? Anyone else that they have a guess what B does? Yeah?
That stretches it horizontally.
That's a horizontal stretch. Remember, A and B are backwards from what you would expect. If you add with A, it's going to move it left. If you subtract A, it's going to move it right. If you put a big number in for B, like 10, you might think, oh, big number is going to stretch it bigger. No. A big number for B actually compresses it. Small numbers for B. Small numbers make it bigger. So A and B are always the opposite. C and D are not. Okay? What would C do? It's multiplication, but this time it's outside the function. So we know what multiplication inside did. What about multiplication outside?
Vertical stretch.
Vertical stretch. Multiplying is always a stretch. Outside, it's a vertical. Now we're up to D. D is adding, or it could be subtracting. And we know what adding and subtracting did inside. What does it do outside? Yep. That's a vertical shift. And I did A, B, C, D because if you have to describe the transformations, that's the order you do them in. Horizontal shift, stretch, vertical stretch, shift. Now, does anybody remember what would happen if B was a negative? What does a negative cause to do?
It causes it to flip.
It causes it to flip horizontally. This is an example of a horizontal flip. That's a horizontal reflection. So if B is negative, it's a horizontal reflection. If C is negative, it's a vertical reflection. Vertical reflection would look like this. That's a vertical reflection. So vertical means over the x-axis, horizontal means over the y-axis. So there's 6 things potentially that could happen in a transformation problem. 2 shifts, 2 stretches, 2 reflections. So these transformations, I'm just saying here, it's very similar to all the transformations we've studied all year. So I want to know how to sketch g of x where the parent or the base function is square root of x. Okay. How many transformations out of 6 are taking place in g of x? Chris?
2.
No, not 2.
1.
Just 1.
Yeah, okay.
There's just 1 transformation here. So to sketch g of x, what would you have to do to the original? Like if you had the original on a piece of paper, what would you do to it to change it into g of x? What is that minus 2 doing? Shifting it, stretching it, reflecting it, and then which way? How much? Up, down, left, right? Horizontal shift, which way and how much? Okay. So it's going to sketch g of x, shift square root of x, 2 units right. Now, when I did this last week with my juniors, I mean, some people wrote like a whole paragraph. Like, you don't really need that much. Just shift 2 units right. That's all you need to say. Okay. All right, let's look at this one. H of x. Okay, so we'll start out the same way. To sketch h of x, what would you have to do to square root of x according to this plus 3? What's that plus 3 going to do? Yep, okay. It's going to move it to the left, how many? 3, yes. So to sketch h of x, shift square root of x, left 3 units. Okay, now look at k of x. What's weird about that one? And look at what I wrote on the very top line. And now compare what I wrote there to k of x. What's strange about k of x? Yep.
You have a negative variable.
That's okay, we can have negative variables. But there's something weird about how I wrote that.
Oh,
Yeah.
you have the variable after the constant.
Yeah, we don't normally like to write it that way. You want to write it variable, then constant under the root. So let's fix that. Square root of negative x plus 3. Now, Caleb, how many transformations are happening here?
2.
Yes, there are 2. The 3 is doing something, the negative is doing something. Well, we already know what the 3 is doing. That's the same as the one above. Shift 3 units left. And the reason I wrote that one first is because it's in the position where the A is. I didn't do the negative yet because that's in the position where B is. B is second. So don't describe that one first. So shift 3 units left. Now, what's that negative going to do? Yep, Emma? Yes, that's a horizontal reflection. Another way to say a horizontal reflection is over which axis? Gotta be a little careful here. The horizontal goes like this. Yep.
The Y.
It's over the Y. If you flip horizontally, you're flipping over the Y. So if you wrote reflection over Y-axis, that's fine too. That's it. Any question on that? Okay, so describing transformations, same old kind of thing. All right, so now we're going to get into some sketching, and then the last thing we'll do is we'll solve a couple equations. So, what I want you to do when you're sketching is always sketch the point that corresponded to 0, 0. For an even root, that's a start point. It's this point right here. For an odd root, it's the center. Okay, so what I'm basically saying there is, tell me where it starts, or tell me the center, if it's an even or an odd root. Now remember, there are no asymptotes in these functions. Another type of function we're going to look at later in the week looks similar to that, but it has asymptotes. Okay? And on the test, people mix them up. So just try to remember, roots, no asymptotes. I don't know how to help you remember that, but root functions have no asymptotes. So, when you transform a function, shift it, stretch it, whatever you do, you're going to have to find a new x and a new y value for the starting point, or the center point. Depends what you're doing. To find the x value, take the radicand, which in a problem like this would be what I just circled. Take that radicand and set it equal to 0. Solve it. That will tell you the x value of the point. Now, once you have the x value, finding the y value is pretty easy because you're going to have a formula like this. If you said to me, oh, x is 5, well, all I have to do is take and plug in 5 for x, do out this arithmetic, and that'll tell me y. So to find the y value, substitute what you got for x back in. Now, that point by itself isn't enough. That's only one point. You need some more. How many more? Depends. Depends on the problem. So get some more points. Use the table on your calculator. Now, why did I say include points to the left and the right, if applicable? Why did I put if applicable in parentheses? Jared?
Because if it's just a even, it's not going to go to the left.
Yeah, well, remember, you could take an even and mirror image it. So an even could look like this. It could.
Yeah. Well, it's
It's
only
only-
going to be in one.
Yeah, it's only going to go one way, right? So if you have an even root, it's only going to go one way. If you try plugging in numbers on the wrong side, you're going to get imaginary answers. It's not going to work. Right? If you have an odd root, yes, check on both sides of your center point. Both. So let's take a look at this one. Before I do any math at all here, is this going to be a root that goes in one direction or both? Okay, it's going to go in both. It's an odd root, so I'm going to find the center, and then I'll check points on both sides. So, how do I find the x value of my center? What was the step for that? Jared?
Set it equal to 0.
Set what equal to 0?
Or the whole equation.
No, not the whole equation. Just the
No, it's under the,
Oh.
what's under the root.
yeah.
Just the radicand. So we had that. Set radicand equal to 0. So Eric, what's my radicand here? Oh, you know what? I think did I skip one?
Yeah, I think you just scrolled down.
Oh, I just scrolled down. Okay, let's do that. Let's do this one first. What's my radicand there?
3 minus 2x plus, or just that.
Just that. Set that equal to 0. Solve it. Take my minus 3 from each side, divide by 2. What's my x value? Let's do it as a decimal because that's easier to graph.
Decimal 1/3. 1/6. 2/3. Be 2/3.
What's it going to be as a fraction?
2/3. What be done? Yep. 3/3. Oh my God, 3 halves.
3 halves, yes. And then 3 halves as a decimal. What's 3 divided by 2?
1.5.
Okay.
1.5.
1.5. Okay, so I'm going to make a table off to the side. 1.5 is my x. Let's find my y. Now, I said use substitution to find the y. You really don't have to. Watch what happens. What's 2 times 1.5?
3.
3. What's 3 minus 3?
0.
What's the cube root of 0?
0.
What's 0 times 2?
0.
So your y value, 0 plus 1, is plus 1. So the y value is really just the number at the end. You don't even have to do all that out. Okay, so that's 1 point on our graph. Right, so let's start to make a sketch. 1.5, comma, 1. All right, so let's grab this. And our first point, 1.5, comma, 1. Okay, so we got that. Now, that's 1 point. I need more. I could get more by hand, plugging in values for x. A lot easier to use your table. So, let's go to our calculator, and let's put this all in. So I'm going to show you how to type that whole thing in. This is how you have to type it in. 2 times 3 math 5. 2 times the cube root of 3 minus 2x. Make sure you get out of the radicand, and then do a plus 1. One way we can check that we typed it in right is in my table. I'll put in 1.5 and see if I get 1. Let's go second table, 1.5. Yep, I get 1. So earlier I asked you guys, is this going one or both directions? It goes both. So you want to check points above 1.5 and below. Like, you don't have to check 2. I mean, that's pretty close to 1.5. Let's check like 3, 5, 7, 9. Let's try hitting enter. 5, 7, 9. That should give you a pretty good idea of what it's going to look like on one side. Now let's check the other side. Let's do 0, -2, -4, -6, -8. That's great. That's a lot of points. We should get a pretty good sketch out of that. Okay, let's see what it looks like. 3, -1.8. 5, -2.8. Let's see, 7, -3.5. 7, think about right there. You can kind of see it starting to curve. And 9, -4. Okay, so that's good for one side. Now let's do the other side. 0, 3.8. -2, 4.8. 1, 2, 3, 4.8. About right there. -6, 6 basically. 5, 6 looks good. And -8, 6.3. Okay, about right there. Now connect all your roots, and that's the graph of your root. And so something kind of like that. Let's hit graph and see how I did. Might have been a little steeper in the middle than I drew it, but I think that'll look decent. So it should cross the y-axis. That looks good. Comes down. Yeah, that's pretty good. That's good. So that's a cube root. Any questions on that? Okay. Let's look at this one. I'm not going to actually sketch it. I just want to solve for the point. And then I want you to tell me some points I could plug in. Okay, but I'm not going to do the whole sketch. All right. What's my first step to get the x value? What do I do first? Okay.
So that's the stuff you have circled to 0.
Yep. Set that equal to 0. So x is about 1 1/3. Okay. For graphing, basically 1.3. Now, based on the trick that I told you guys, what's my y value going to be?
-2.
Yeah, because when you plug back in for x here, you already know it's going to come out to 0 because that's what you forced it to be. So when you plug in the x, you're going to get 0. 4 through to 0 is 0. 0 times 3 is 0, minus 2. So we're going to get 1.3 and -2. Now, this is an even root. One direction or both? One. So we only can pick values going one way. either bigger than 1.3 or less. If you're not sure which way, pick a number in your head right now that's bigger than 1.3. A simple number to work with. Plug it in for x and see if you can take the fourth root of the number you get. Right? Can't come out negative. If it comes out negative, then it's imaginary. You went the wrong way. So what kind of values can I pick for x here? Bigger or smaller?
Getting smaller.
They have to be smaller. Try plugging in 2 for x. Look what happens. If you plug in 2 for x, what's 3 times 2? 6. What's 4 minus 6? Negative 2. Can you take the fourth root of negative 2? You can't take a root of a negative number if it's an even root. If it's an odd root, that's fine, but not for even. So you plugged in 2 for x, you picked a number on the wrong side of 1.3. Pick numbers that are smaller. So numbers I would pick, I would probably do 0, maybe negative 2, negative 4, negative 6, negative 8, negative 10. If you do those 7 points, that should give you a pretty good sketch. It's going to look something like this. It's going to curve to the left. And you might be like, well, why does it curve to the left? I thought roots always curve to the right. There's a reflection right there. If you wanted to write down all the things that are happening in this one, there's 1, 2, 3, 4, 5 things happening out of the 6. It's a shift of 4 units to the left. It's a vertical compression by a factor of 3, horizontal. So horizontal compression by a factor of 3, horizontal reflection, vertical stretch by a factor of 3, and then shift down 2. They didn't ask for all that, but this one's got it. It's got a lot in it. Okay. But that reflection is what's going to make it curve to the left. Okay, so last thing we're going to look at is solving some radical equations. The more radical equations you have, or the more radicals in the equation, the more of a problem it's going to be. Okay. Just to show you guys an example, that's an equation with 1 radical. That's an equation with 2. That's going to be more of a pain. You're never going to have more than 2. But the goal is make sure when you start the problem, one of your radicals is already by itself. If it's not, you have to get it by itself. And then what we're going to do is we're going to cancel that radical out using a power. What power? You're going to use the power that would cancel the root. So for example, if you had a square root, you use the square power, power of 2. If you had a cube root, you have to cube, power of 3. Okay? You also always have to check for extraneous solutions. Okay? Remember, extraneous means you didn't do anything wrong, but one of the answers that you got doesn't work. Okay? So we always have to check for that. So let's solve this one. Okay? This one's actually not that bad. Right? Even though it's a cube root, you might think, well, is that harder than a square root? That could be, but the nice thing is there's only one of them. This problem is harder. Even though it's a square root, it's a simpler root, it's still harder than this one. So, it says isolate the radical. Brandon, is my radical isolated there?
Yeah.
Yes, it is. There's nothing on the left-hand side outside the radical like this. You wouldn't want something like that. Okay, you'd want to move it to the other side. But we're good. So what can I do on each side to get rid of the cube root?
Raise it to the power of 3. Or
Raise-
raise each side.
Raise each side to the power of the root you're taking. We're doing the index is a 3, so let's cube it. Cube, cube. Cube root and cube is gone. X squared minus 2x plus 2 equals x cubed. Now, we're going to want to try to solve this by factoring. Anytime you factor, you always get it equal to what number?
0.
Get it equal to 0. I think the easiest way to do that, because I like to always have the biggest term positive, is move everything to the right. So 0 equals, we've got x cubed. Elias, what else would be on the right-hand side?
7.
What else would be on the right-hand side if we put everything on the right?
X squared.
What kind of x squared?
Negative X squared.
Negative x squared. Yep.
2x.
Plus 2x
And minus 2.
minus 2. Now, does anybody remember the kind of factoring you can try with 4 terms? It's 3 words, blank, blank, blank. Factor blank by grouping. That's the only type of factoring you can try with 4 terms. If that doesn't work, we're going to be kind of stuck. Right? So look at the first 2 terms. What do those have in common that I could factor out? Okay? X squared. If I factor that out, I'm left with x minus 1. I'm hoping magically to get another x minus 1 in this problem. That's how factor by grouping works. Okay. What can I factor out of 2x and minus 2? Yep. 2. If I do that, I'm left with x minus 1. Perfect. Now, look at what I just underlined in red. That's term 1. That's term 2. Caleb, what do both of those terms have in common now? They both have x minus 1. This is how factor by grouping works. Now, factor that out of both. If I factor it out of the first one, all I'm left with is an x squared. If I factor it out of the second one, all I'm left with is a plus 2. So now we have 2 factors. Factor 1, factor 2. What do I do with each of those factors? Emma? Set them equal to 0. Okay, that one's easy enough. X equals 1. Let's do the other one. Subtract 2. How do I undo squaring? Chris?
Square root.
Square root. Take the square root of both sides. And what's the square root of negative 2?
Imaginary.
It's imaginary, so we're not going to bother with it. So the only answer that I got is 1. I still have to check if it works. Let's plug it back into the original problem. What's 1 squared? 1. What's 2 times 1? Minus 2 plus 2. So we're going to take the cube root of that number. What's 1 minus 2? Negative 1 plus 2. And what's the cube root of 1? 1 equals, and we plugged in 1. 1 cubed is 1. So yeah, it works. The answer to that is x equals 1. Any questions on that one? Okay, let's look at this one. Now, do I have a root all by itself on one side this time? Sam?
No.
No. What I would do is this. Keep this root where it is. Add the square root of 4x plus 9 to both sides. So now you've got this. Now I have isolated one of my roots. Now, to get rid of this root on the left, what power would I raise each side to?
2.
2. We're going to square each side. Remember, side, not terms. Side. That's very important because you're going to do this. When you do it on the left, all you get is this. That's the easy one. When you do it on the right, you're going to get this. This, I'm writing it out the long way, times this. What's the name for how you do that hope?
Foil.
Foil. You have to foil. That's what makes it a little bit of a pain. But this is the worst step. After this step, it gets easier. 6x plus 12. Okay. Jared said foil, so multiply the first. Eric, what's 1 times 1?
1.
1. So that part's not bad. Jacob, what's 1 times the square root of 4x plus 9?
4x plus 9. Or the square root of 4x plus 9.
Square root of 4x plus 9. And what's the inner 1 times the square root of 4x plus 9?
The same.
Same thing. So how many of them do you have?
1. Or you would have 2.
You have 2. You have 1 times the square root of 4x plus 9, another 1 times the square root of 4x plus 9. So you have 2 of the square root of 4x plus 9s. And the last part, what's the square root of 4x plus 9 times the square root of 4x plus 9? It's basically like doing this.
And then just
You're multiplying the square root of 4x plus 9 times itself.
wouldn't it just be 4x plus 9?
4x plus what?
9.
Yep. Now, it looks like it got a lot worse, but once we combine like terms, look at how many roots you have in the problem now. You had 2, now you have 1. That's better. Okay. Let's combine some like terms. What's 1 plus 9? 10. Plus this term, plus this term. Now, we're going to do the same thing again. Get this square root by itself, and then we're going to square both sides. What's one thing I could move to the other side to start to get this by itself? It's 3 things I have to move, but let's do one at a time.
10.
Yep, how would you move to 10?
Minus 10.
All right, we'll do that. Let's do something else at the same time. What's something else I could move? Not yet. That's going to have to be the last thing you move. But we are going to move it. Yep.
The 4x
How would you move that?
minus 4x.
Yep. Minus the 4x. Minus the 4x. Now it's going to get a lot simpler. Let's see what we have now. 2x plus 2 equals 2 square roots of 4x plus 9. Now, how could I move that 2 to the other side?
Multiply by 2.
If you multiply everything by 2, you're going to get 4x plus 4 equals 4 square roots of 4x plus 9.
Divide.
Divide. So divide by 2, 2, 2. That gives you x plus 1 equals the square root of 4x plus 9. Now we have the root by itself again. What am I going to do on both sides?
Raised to the power of 2.
Raise each side to the power of 2, and now, when you do it this time, all your roots are going to be gone. Okay. Can anyone tell me what you would get on the left if you FOIL that out? Some people need to see it. If you need to see it, do it like this, off to the side. X, yep, x squared. And what else are we going to have there? A plus 1, and there's one more thing, because we have to FOIL it out. Yep,
2x.
2x. X squared plus 2x plus 1. And How about Eric, what's gonna be on the right?
4x plus 9.
Yeah. Now we've got a pretty straightforward equation. No square roots in it. It's a quadratic. Let's get everything on one side and get it equal to 0. So we're going to have x squared. I'm going to minus 4x from each side. And I'm going to minus 9. And hopefully that factors. Two numbers that multiply to give me 8. Subtract to give me 2, 4, and 2. So let's give it a shot and see what happens. X plus minus, let's try 4 and 2. X squared minus 4x plus 2x. Yep, 2 times negative 4 is negative 8. Perfect. So, 2 answers for x. Sam, what's my first answer?
-2.
Yep. And Mikara, what's my second answer?
Positive.
Positive 4. Remember, we just have to check and make sure it works. Let's check 4 first. And checking is usually, that part's pretty easy. What's 6 times 4? Plus 12? What's the square root of 36? Okay, just gonna put that off to the side. 4 times 4? 16 plus 9? 25, square root of 25? 5. Is 6 minus 5 1? Yes, then that answer works perfect. Let's check negative 2. What's 6 times negative 2? Negative 12 plus 12? And the square root of 0? This isn't looking good. 4 times negative 2 is negative 8. What's negative 8 plus 9? What's the square root of 1? Is 0 minus 1 equal to 1? No. So if you did all this work and you left both these answers circled, I'd take 1 point off. What you'd want to do here is cross this out and write extraneous. It just means that it's an answer that did not work. Okay. But that is by far the hardest one that we do. So that's definitely the hardest one. Okay, so last one is just a calculator one. So it says solve graphically. Right, how am I going to solve this graphically? Can someone tell me just the strategy? What am I going to try to do? Just kind of one step at a time. Yeah?
I would put the left part in one equation and the right part in another equation.
All right, let's start with that. So we're going to put the left part in one. We're going to put the right part in the other. Can somebody help me type in the left part? What do I have to, what are the buttons I have to press to get all that typed in? Yep. Yep. Option 5. Okay. All right, so we got the left. That's the hard one. I think the right everybody can do. X squared plus 1. All right. And now I'll do zoom 6. I think that'll be okay. So this is a 5th root. So it does go in both directions, but it's got kind of a funky look to it because you got a variable that's squared. When you square a variable, that makes it look really funky. If you got rid of that square, it would look more like the S shape. Okay, let's look at that. Okay, so what am I'm looking for where the 5th root, that's what was in blue, is greater than or equal to the red. Is the blue ever greater than or equal to the red?
Yes.
Yeah. In like a small section or a big section, can someone describe where? Yep, Chris?
Name one. Around like -1 to 1.
Around like -1 to 1, yeah, we just have to figure out what those points are. But it's somewhere in the parabola, in the U. That's what we're looking for. Now, when I write my interval, will it have brackets or parentheses? Brackets, because it can equal. How am I going to figure out those two numbers that Chris estimated that were like -1 and 1? How am I going to get them exact? Yep, Chris?
Use second cal intersect.
Yep, second calc intersect. Okay, I'll do the one on the left. I mean, it looks symmetrical, so I'm guessing the one on the right is going to be the same but positive. But if someone could double check the one on the right, that would be helpful. So I got -0.73 for the one on the left. Is the one on the right positive 0.73?
Yeah.
It is? Okay. So from -0.73 to positive 0.73. The graph in blue is above the graph in red. Everywhere else, the graph in blue is way lower. The red graph goes up way, way higher. Okay, so something we've done before, finding an intersect, we're just doing it with a radical rather than the other kind of functions we've studied all year. Okay. Any questions there? Okay, so that's pretty much all we do with radicals. Showed you a little bit of graphing, a little bit of equation solving. But tomorrow we're going to look at our second to last type, which is exponentials. Okay, so homework tonight, it kind of jumps around a little bit. Still, it's not a ton of questions, but it just jumps around. So it's 5, 6, 12, 14, 20 to 22, and 28, 31, 35. I think it's like 10 or 11 questions, something like that.